For each pair of problems, find the quotient by factoring the numerator, then find the second quotient by using the first one. So we have to factor the numerator here for this first quotient. So what multiplies to negative 14 that adds to negative 5? Well, that's x minus 7 and x plus 2 divided by x plus 2. Oh, and notice that they have a common factor there. So those x minus 2's divide to 1, and I'm left with x minus 7. So that quotient is x minus 7. So somehow I need to use this quotient to help me factor this expression, to help me divide that expression. So I'm going to look at the numerator and say, wait a minute, that's really x squared minus 5x, not plus 2, but minus 14. But I need that to be a plus 2, so plus 16. Minus 14 plus 16 is the same exact thing as x squared minus 5x plus 2. I just rewrote that 2 in an equivalent way. And then we divide. I'm going to treat that as one chunk up there, that trinomial. Well, what's x squared minus 5x minus 14 divided by x plus 2? Well, it's x minus 7 because we just found that quotient. And what's my remainder? I'm left with 16 over x plus 2. So the answer is x minus 7 plus 16 over x plus 2. I had a remainder of 16. Number 2, x cubed plus 1 over x plus 1. So I want to factor the numerator. Well, that's the sum of perfect cubes. So that factors into x plus 1 times x squared, opposite sign. So minus x times 1 is x plus 1 over x plus 1. Well, x plus 1 is a factor of both the numerator and the denominator, so I'm left with x squared minus x plus 1. That's what the quotient is equal to. So how is this related to this quotient, the second quotient here? Well, if I add plus 1 and minus 1 in the numerator, I really don't change the value. X cubed plus 1 minus 1, that's the same thing as x cubed. And I'm going to divide that by x plus 1 still. I know what the quotient of x cubed plus 1 over x plus 1 is. That's x squared minus x plus 1. We just found that. What am I left with? Minus 1 over x plus 1. We can only do this because we're treating x cubed plus 1 and x plus 1 as one term and dividing. But truly, you need to be able to divide by using the reverse tabular and long division, either one, not and, or. You need to be able to use the reverse tabular or long division. So for this question, I want you to divide using reverse tabular. The next question, I want you to divide using long division. Cubic divided by an x, and it's going to leave me with an x squared. So I need x squared times x gives me x cubed. So from that term, I get x cubed. This term, I get negative 9x squared. That term, I get 5x. And this term, I get 2. Go through the reverse tabular method. X squared times x is x to the third. X squared times negative 1 is negative x squared. But I want negative 9 of them, and I currently have negative 1 of them, so I need another negative 8x squared. Well, negative 8x times x is negative 8x squared. So that gives me a plus 8x there. I have 8 of them, but I only want 5 of them, so I need another minus 3x there. Minus 3 times x is minus 3x. Minus 3 times negative 1 is 3. Now, notice how I want a 2, but I have 3 of them right now, so my remainder is not 0. What this tells me is x minus 1 is not a factor. X minus 1 is not a factor, so we need to figure out what our remainder is. What plus 3 gives me negative 2? Well, my remainder would have to be a negative 1. So that makes my answer, that makes that quotient in quotient remainder form, x squared minus 8x minus 3, that's our quotient, minus 1 over your divisor, minus our remainder over our divisor. So that's the final answer right there. Find the quotient by using long division. So I'm dividing x cubed plus 2x squared plus 8x plus 1 by x plus 5. Well, x squared times x gives me x to the third, so I multiply through. X squared times 5 is plus 5x squared. Subtract, change my signs, and I get minus 3x squared plus 8x. Well, minus 3x times x gives me minus 3x squared. Minus 3x times 5 is minus 15x. I'm going to change the signs to subtract, and I get 23x plus 1. Restart the long division algorithm. Well, plus 23 times x gives me 23x. 23 times 5 is 115. I change my signs to subtract, and I get a remainder of negative 114. I get a remainder of negative 114. So my answer, that quotient, is equal to x squared minus 3x plus 23 plus my remainder, so minus 114 over x plus 5. Number 5, find this quotient. Let's do that first. Let's first find that quotient before we move on. So I'll do long division for this one. X cubed, wait, I need a placeholder, plus 0x squared plus 2x plus 11. X squared times x is x cubed, minus 2x squared. Change the signs to subtract, and I get 2x squared plus 2x. Well, plus 2x times x gives me 2x squared. 2x times negative 2 is negative 4x. Change the signs to subtract, and I get 6x plus 11. Well, plus 6 times x is 6x. Minus 12. Change the signs to subtract, and I get 23. So that tells me my final answer, my quotient, is x squared plus 2x plus 6 plus my remainder, 23, over x minus 2. That's that quotient in quotient remainder form. Now let's look at f of x. Find f of 2. Well, f of 2 means plug in a 2. 2 cubed plus 2 times 2 plus 11. 8 plus 4 plus 11. 12 plus 11 is 23. Explain what you observe. Well, we had a remainder of 23, and f of 2 was 23. So somehow these two ideas are related. Somehow dividing by x minus 2 and finding f of 2, because those two are the same, somehow have to be related. Number 6, let p of x equal x cubed plus 2x squared plus 2x minus 5. Divide p by x minus 1. So let's do that first. Let's divide p by x minus 1. I'll do reverse tabular for you reverse tabular people out there. Cubic divided by a linear term is going to be quadratic, because x squared times x gives me x cubed. I know that has to be an x cubed. This needs to be a 2x squared. It's now 6th period. 2x and negative 5. So x squared times x gives me x cubed. That gives me a negative x squared there. I want 2x squareds. I currently have minus 1 of them, so I need 3x squareds there. Well, plus 3x. 3x times negative 1 is negative 3x. But I want 2 of them. I have negative 3. So that gives me 5x plus 5. 5 times negative 1 is negative 5. So, do I have a remainder? No, my remainder is 0, which is good because that means my quotient is x squared plus 3x plus 5. What that tells me is x minus 1 is a factor. X minus 1 is a factor. Find p of 1. Well, p of 1 means plug a 1 in. So 1 cubed plus 2 times 1 squared plus 2 times 1 minus 5 equals 1 plus 2 minus 5. 5 minus 5 is 0. Well, this is interesting now because we saw that x minus 1 is a factor, which means I have a remainder of 0, and p of 1 is 0. So there has to be some kind of relationship here between our factors, our remainders, and our zeros, and that's what we get to explore in lesson 15. Number 7, knowing that x minus 3 is a factor of p of x, factor p into the product of 3 linear factors. So because x minus 3 is a factor, I can divide by x minus 3 to find the other factor, and hopefully I can factor that one. I need a negative 11x squared from that diagonal, a 4x from that diagonal, and a 60 from that diagonal. X squared times x is x to the third. X squared times 3 is negative 3x squared. I want negative 11, so I need minus 8 more of them. Restart the process. Minus 8x times x is negative 8x squared, which gives me plus 24x there. But I only want 4 of them, so I need a minus 20x up here. Minus 20 times x is minus 20x, which gives me 60. Don't get into the habit of just saying, oh, double check, make sure there's no remainder. 60, I want 60, my remainder is 0, which is good, because that means x minus 3 actually is a factor. What this lets me say now is p of x is x minus 3 times x squared minus 8x minus 20, because we multiplied this times that to get the product of p of x. Well, I want to factor into 3 linear terms. Currently, I have 1 linear term and a quadratic term. So how do I factor that quadratic term? Well, what multiplies to negative 20? That adds to negative 8. Well, that's negative 10 and 2. So that tells me that p of x can be written as x minus 3, and then we factor the quadratic term into x minus 10, x plus 2. So those are the 3 linear factors of p of x. Describe the end behavior of f of x. Well, end behavior says what happens as I plug in really positive numbers. As x goes to infinity, what happens, and what happens as x goes to negative infinity. There's 2 things that determine end behavior: the leading coefficient and the degree of the polynomial. This is an odd degree polynomial, so we have 2 choices. It's going to look something like that, or it's going to look something like that. You can do the little dance with your hands right now. Because it's an odd degree, I know it has either one of those 2 end behaviors. And my leading coefficient's positive, so that means it's this choice here. As x gets really big, what happens to my y values? My f of x values approach infinity. Because overall, draw it bigger, this function has the shape of x cubed, something to an odd power. And as x approaches negative infinity, my y values go also to negative infinity. Great, so that's how I describe the end behavior. Is it even, odd, or neither? So, if a function's even, it's symmetric across the y-axis. If it's odd, it's symmetric about the origin. Neither is if it's neither one of those 2. That's how we can test it graphically. And please feel free to graph f of x and see which symmetry it has, if it has any. Or we can do the algebraic test by saying f of negative x. What happens when I plug in a negative x? Well, I get 4 times negative x to the 7th plus 3 times negative x to the 5th plus negative x. Well, a negative to an odd power is going to be negative, so negative 4x to the 7th. Negative to an odd power is still negative, so minus 3x to the 5th minus x. Well, I didn't get the same thing. I didn't get my original function back, so it's not even. But we did get the opposite of our function back. We got negative 4x to the 7th plus 3x to the 5th plus x if I factor out that negative 1. So we didn't get f of x back, we got minus f of x back, which is the definition of an odd function. If you plug in f of negative x, you get back negative f of x. That's just the algebraic way to see odd, which means it has symmetry about the origin if you looked at it graphically. Number 9, factor completely. Well, whenever we factor, we look for a GCF. The only GCF is 1, so that's pointless to factor out. There's 4 terms, so I have to group. Let's group the first 2 together. Z squared, I'm left with z minus 2. Hopefully I can end up with a z minus 2. So what do I need to factor out? Negative 1. Now my new GCF is z minus 2. Undistribute that and you're left with z squared minus 1. But wait a minute, that's the difference of perfect squares. So z minus 2 times z plus 1 times z minus 1. Factored completely, these 2 expressions are the same. They look different, but they're actually the same exact expression. Number 10, sketch a graph of g of x without a calculator on your own set of axes below. So, I'm going to draw a set of axes. By using its zeros and end behavior. Well, the zeros are easy. The zeros occur at, well, if x plus 2 is a factor, x equals negative 2 is a 0. And the other 0 is at x equals 4. But this has multiplicity 2, because it's a repeated factor, and this 0 has multiplicity of 3. Remember, even multiplicities are tangent to the x-axis. They kiss the x-axis and then turn around. Odd multiplicities cross through. So I know at -2 and at 4, I have a 0. So I know my function has to pass through the x-axis only at those points. End behavior-wise, well, what degree polynomial is this? That's x squared and x to the third, so it's a degree 5 polynomial. Degree 5, and my leading coefficient is 1. So it's going to look something like this. As x approaches infinity, it's going to go off that way, and as x approaches negative infinity, it's going to go down that way. So now we can fill in the gaps. It touches -2, but then it has to turn around because it has that even multiplicity. It turns around and eventually has to touch 4 and cross through it, and then it goes off to infinity. So if you were to graph this using Desmos or your TI-84, you're going to get a function that looks like this, and this is an important skill that you get going forward in your mathematics career, to look at a function like this and say, what does it actually look like? That was lesson 14.